Before I move on to the new materials, I want to do a little recap from what we did last week. Last week, we began with optimization of functions. In particular, we focused on maximizing an objective function in n variables. And we discussed two situations. Firstly, is when you're given a collection of equality constraint, equality constraint, which I call GI equals to AI. Another situation is when you're given a collection of inequality constraint, and then the inequality are given by xj less than or equal to bj. So let me emphasize that the inequality sign here is important. It must be less than or equal to, okay? It's a must, okay? And then how do we deal with this constraint problem? The first thing we need to do is to write down the Lagrangian function. And then by convention, okay, the Lagrangian function for equality constraint, the Lagrange multiplier involved, we will use the mu I to denote them. And whereas for inequality constraint, we use lambda j to denote the Lagrange multiplier. And after forming the Lagrangian function, then we have to write down the first order condition. For equality constraint, it's easier because basically what you need to do is just to differentiate the Lagrangian with respect to every single variable, including the Lagrange multiplier, and set them to equal to 0. Then that will give you the first order condition under equality constraint. However, the situation for inequality constraint will be much more complicated. Firstly, you only differentiate L with respect to x1 up to xn, okay? No lambda I, okay? No lambda I at all. And then, but how about the lambdas? The lambdas, you will replace them by so-called complementary slackness condition. That is given by lambda j times xj minus bj equals 0 for every single j. And this is called complementary slackness. And last week, I gave you the motivation of why this should be true. But that's not all, okay? Because these are inequality constraint questions, then of course they come with all the given inequality constraint, okay? And finally, what is more exciting or interesting is that for inequality constraint, you also have an extra condition that all your Lagrange multiplier are non-negative. Therefore, under the inequality constraint situation, you have 4 kinds of first order condition. It's very easy to miss some of them, so please practice with the homework question last time and make sure that you write down all the first order condition without missing any of them. Last week, we also defined what it means by NDCQ, non-degenerate constraint qualification. That is to make sure that the optimization problem that I deal with do not contain any exceptional point. So how do I check NDCQ in each constraint situation? Firstly, if under equality constraint, then you just need to check the Jacobian matrix. So the Jacobian matrix is formed by, the rows are formed by gradient of the constraint function. Okay? And then you want the Jacobian matrix to have full rank in order to satisfy the NDCQ. What does it mean by full rank? That means that the rank equals to the exact number of the constraints. For inequality situation, it's very similar, but what you're concerned is not all the constraint function, but only those that come from binding constraint. So you're only interested in the Jacobian matrix formed by binding constraint, and you want this matrix, again, has full rank. Or in other words, the rank equals to the number of the binding constraint. Okay? So this is basically what we did last week in a nutshell. And what we're going to do today, the first thing we're going to do today is to combine these two together. Okay, so let's get back to the lecture notes, okay? The first thing we're going to do is to study so-called mixed constraint problem. So in other words, we have both equality and inequality constraints. Let's look at a standard form of this problem. Suppose we want to maximize, okay, it's very important, we try to maximize an objective function subject to two kinds of constraints. The first kind is given by g equals to ai, so these are equality constraint. Okay, and also subject to another collection of inequality constraint. And then how do we deal with that in this case? Actually, there's nothing new. We just need to combine all the techniques that we learned last time, okay? So, for example, how do I form the Lagrangian? The Lagrangian is formed by the objective function minus the sum of mu I times gi minus ai. And then, sorry for writing this again, but as I mentioned, we use mu I, that's just the convention, we use mu I for the equality constraint. And whereas lambda j refers to an inequality constraint. Okay? So the way to form the Lagrangian is just, it's like combining the two situations together. So f, the objective function, minus Lagrangian multiplier times the function coming from the equality constraint minus the Lagrangian multiplier times the function arise from an inequality constraint. And then what are the first order conditions? So because in this situation, you have equality constraint, so besides just L differentiated with respect to all the variables, you also have L differentiated with respect to the Lagrange multiplier coming from equality constraint, i.e. mu I. Okay, so just mu I. So just mu I, which comes from an equality constraint. Okay, but how about the lambdas? The lambdas refers to Lagrange multiplier with an inequality constraint, and then instead of differentiating them with respect to those Lagrange multiplier, we replace them by complementary slackness. So complementary slackness for just the inequality constraint. So this is given by equality of the form lambda I times hi minus bi equals 0. So this case, just for the lambda j, which are the inequality constraint. Okay? And then we have inequality constraint that are the given inequality constraint. So these are the given inequality constraint. Okay? And finally, the positiveness of Lagrange multiplier. But remember, we only require the lambdas to be positive. We don't require the mu to be positive. So only for lambdas. Lambda j, because lambda j come from inequality constraint. We don't have such requirement for mu I, because mu I come from equality constraint. And then, what is NDCQ in this case? NDCQ would be formed by a Jacobian matrix whose rows are given by gradient of equality constraint and also binding inequality constraint. And then we require this matrix to have full rank. Okay? So basically, for mixed constraint, it's really just a mix of techniques that we've learned in both situations that we met last week. Of course, talking like this will become very complicated. On the next page, we'll go over work example together and try to clarify the situation.